Hello, welcome back to AP Calculus. We are in Unit 4, which is all about advanced differentiation techniques. And for the last couple lessons, we focused on two kind of styles of related rate problems. This time, we're going to look at just a variety of them in this lesson. So we'll see a nice mix of all the different types that we've talked about. Let's start with an example problem. 136 pi cubic centimeters of dough is in a cylindrical shape while being rolled out under a baker's hands. While rolling, the length of the dough cylinder is increasing by 2 centimeters per second. Volume equals pi r squared h, and area is 2 pi r squared plus 2 pi r h. Again, they're giving us the formulas that we need. What is the rate of change in the radius of the dough cylinder when the length is 34 centimeters? Well, I don't really know the area right here, but I can use the volume because I know the volume is 136 pi centimeters cubed of dough. So let's start with that. So I'm going to say volume is equal to pi r squared h. And we're going to take the derivative with respect to time. So that's dv dt equals, okay, I need to use the product rule here. So with the r, it's 2 pi r h dr dt. Plus, now I need to take the derivative of h, so that's pi r squared dh dt. All right, well, let's fill in what we know. We know that dv dt is 0 because the volume of the dough is not changing as we roll it out. And we're told that the radius of the dough cylinder when the length is 34. So if the length of the dough is 34, that's the height. So 2 pi, I don't know the r yet, but I do know the height. Well, I'll tell you what, we can find the r, though, because we know that the volume of dough is 136 pi cubic centimeters. And we'll just set that equal to pi r squared times 34. All right, so I'm going to divide both sides by 34. Let's see, and by pi. So 136 divided by 34. I wonder what that is. It might be 4, actually. 34 times 4. We'll see. 1, 6, 12. Oh, yes, that was nice of us to just have a nice little problem like that. All right, so 4 is equal to r squared, so r is 2. Very nice. Thank you, math people. All right. 2, and then the h we already said was 34. We don't know the rate of change in the radius, so that's dr dt. Pi times 2 squared, and dh dt we know was increasing by 2. Well, if I'm rolling out dough like this, and it's getting longer and longer and longer, it's probably getting thinner. So I'm expecting a negative dr dt here. And that definitely appears to be what's going to happen. So this is 4, 8. That's 8. I'm going to go ahead and divide out the pi's, though. And divide both sides by pi, and that's gone. And that's gone, right? So let's see here. We have 8. I'll move it to the other side, making negative 8. And then I'm going to divide by 4 times 34. 2 times 2 times 34, which we can reduce to, let's see here, 2 over 34, which is a negative 1 over 17, is the rate of change in the radius, and that is in centimeters per second. So the radius is getting smaller by negative 1/17 centimeter per minute. Drop my pen. All right. Now, let's see here. What is the rate of change in the surface area of the dough cylinder at this moment? Okay, so we need to figure out the rate of change in the surface area. Now, how would we do that? Well, let's start with the area formula, and we'll just go from there. 2 pi r squared plus 2 pi r h. Let's see here. Take the derivative, dA dt. dA dt is equal to, all right, the first term gives me 4 pi r dr dt. The second term gives me 2 pi derivative r is dr dt. So I like to have the dr dt at the end. So I just kind of move it behind the h, plus 2 pi r dh dt. Well, that's a lot of stuff, isn't it? But I think we have all the information we need at this moment, because we got 4 pi, a radius of 2, a dr dt of negative 1 over 17. We've got an h of 34. Oh, you know what? No, that's right. I did this right. Sorry, I'm second guessing myself here. The 4 pi r dr dt, and then this was 2 pi h dr dt plus 2 pi r. Okay, good. Got just a little bit. I got a little skeptical there for a minute, but I think I got it. So 34, and then dr dt was negative 1 over 17 again, right? And then we've got plus 2 pi, and my r is 2, and my dh dt is 2. Okay, lots to process here. Okay, this is a big, long number involving pi, and I don't really feel like doing it. If this was a free response question on the AP Calculus, we would definitely leave it just like that. You got to plug in all the values, but I don't really see any reason for us to be, beating ourselves up over this. So we'll just say that that's the answer, and we'll put the units in centimeters squared per second. But the scientist in me wants to actually know what this value is. I want to know if it's positive or negative. So I was like, I'm just curious. I could. It's the radius is getting smaller, but the height is getting bigger. So, there could be a positive or a negative value here, right? So I'm just going to go ahead and type it in a calculator. 4 pi times 2 times a negative 1 over 17 plus 2 times pi times 34 times a negative 1 over 17. So that's just going to be negative 4 pi. All right, and then we got plus, that's 8 pi there at the end. Okay, I get a positive 11.08. So that doesn't make sense. I am definitely missing a negative somewhere. Okay, I'm about to say, I was like, that can't be right. Well, but it says it is right. Okay, no, it's 11.09. It's a lot bigger than I thought it would be. Well, this is 8 pi, so this is a pretty big number, though. And that's 4 pi. So 4 pi plus 8 pi is 4 pi. And that's a small number. So, yeah, it makes sense. Okay, we'll take it. Let's go on to the next one. A trough is 10 feet long and 6 feet across the top. The ends are isosceles triangles with an altitude of 4 feet. If water is being pumped into the trough at 9 cubic feet per second, how fast is the water level rising when the water is 2 feet deep? All right, we are actually missing a formula here. It would be given to us as the formula for this is area of the base times the height, where the area of the base is the area of the triangle. So let's write our formula for volume. Volume is the area of the triangular base is 1/2 6 times 4. And the height, oh, what am I doing? I'm forgetting that it's not, those aren't constant. All right, as the water is flowing in, let's go back to that. Okay, as the water is flowing in, we're going to have a water level like that. Okay, so in other words, the water is going to be at some height like that will be rising. But this triangle has to be similar to this triangle of water is a similar triangle to the outer triangle. So they have to be in proportion. So I know that whatever this, if I call this B and I call this H, okay, that B is to 6 as H is to 4. Has to be that way. So 4B equals 6H, something like that. And We want to know how fast the water level is rising. So H is the water level. So I need to solve for B. So B is going to be equal to 3 halves H. Okay, so volume is 1 half area of the area of the base is 1 half little base times height. So 1 half times 3 over 2H is the little b, and then times H. Then times the height of this prism, which is a constant 10. So volume is equal to, let's see here, I can reduce this. So 15 over 2h squared. Now we'll take the derivative. dv dt is equal to 15h dh dt. Okay, not bad. Now we want to know how fast the water level is rising when the water is 2 feet deep. We know that the water is being pumped into it at 9 cubic feet, so that's a positive 9 equals 15 times 2 times dh dt. All right, so 9 over 30, which, we could reduce that to 3 over 10, and that is feet per second, is the rate of increase in the water level's height. All right, let's do another one. 2 ships are at port. One travels north at 20 miles per hour. The other travels 2 hours. 2 hours later, the other begins traveling east at 30 miles per hour. That's 2 hours later. Okay, so this one here, I like to call this y, and this x, and this z. We've been told dy dt is equal to 20 miles per hour, and we've been told that dx dt is 30 miles per hour. Now, there is a delay in when x leaves, but the rate of change in x is still 30. What is the average rate of change in the distance of the 2 ships 4 hours after the first ship begins to leave north? So let's write our relationship. The distance between the ships can be compared with the Pythagorean theorem, making this 2x dx dt plus 2y dy dt equals 2z dz dt. All right, and then I'm going to divide everything by 2. So goodbye 2, goodbye 2, goodbye 2. All right, we need to figure out what x and y are after 4 hours of traveling. So one travels north 20. The first travels for a full 4 hours, right? 20 miles per hour for 4 hours. So we know that that is 80. And dx, that's the wrong one, y'all. That's going to be, we say 80, and then this was 20 miles per hour, right? The other one leaves 2 hours later. So 2 hours later, meaning at 30 miles per hour, 30 times 2 hours out of the 4 would be 60. So this is going to be a 60. And its dx dt is 30. And that's going to equal z. Well, this is, we said this was 80 here, and this was 60, which is 86. This is a 3, 4, 5, or 6, 8, 10, but everything's been multiplied by 10, so 100. So that's 100, and we are looking for dz dt. So we just got some calculating to do here. I can divide everything by 10, though. Just a little bit of number sense here, and it gets rid of all those zeros. Then I'm going to divide by another 10, and that gets rid of those zeros. So it ends up being 18 plus 16, which is what, 34? So 34 miles per hour is the rate of change. What is the rate of change in the angle theta shown in the diagram? Okay, well, we can actually use any trig ratio. I always say you want to use a trig ratio that involves a constant, if possible, and then one of the sides that you know the rate of change for. Well, we now know the rate of change for all of them, right? We know the change for all 3 sides, and none of the sides are constant. So we might as well just use whatever you're comfortable with. I'm going to just go with, well, I don't know. How about sine? Let's try sine. The sine of theta is equal to y over z. So the cosine of theta d theta dt, because of the chain rule, right, equals, now I got to use the quotient rule because I had stuck with a fraction with y's and z's. So this is low d high. So dy dt times z. Low d high minus high d low dz dt. All over low low. All right, there's a lot here, but we ought to be able to figure everything out. This is at this moment, it may not say that, but we mean at the same moment, right? Remember, this was a 6, 8, 10 triangle. In other words, this was a 3, 4, 5 ratio. So the cosine of theta is 3 over 5. Z at this moment we said was 100. Dy dt we know earlier was 20. Then y was at this moment, what was it, 80? Yeah. And then dz dt we found earlier to be a positive 34. And this is all over 100 squared. So we got a lot to do. And I don't, again, if it's a free response, I would just multiply both sides by 5/3. You don't want to give them a chance to count off for arithmetic mistakes, and they don't want you to do them anyway. I've looked at the grading. I haven't graded it myself in the AP exam, but I've looked at it. You could see they make comments on it like, student earned full points. Student continued to simplify anyway. Student simplified correctly, so student earned full points. And then other times you'll see when on the released grading papers with the examples, they'll say at this point student has full points. Student continues to simplify. Student makes a mathematical error, loses points. So it's just never a good idea. And on the multiple choice, yeah, you got to match their multiple choice answers. But there's, they're not going to have numbers this bad usually. And the mistakes are not usually, when we make a multiple choice test, we always put possible mistakes that a student would make for an answer choice. Well, they're going to be calculus based, not arithmetic based. So usually it's not something you have to worry about too much. So it turns out to be negative 0.12. So that's what, negative 12 over 100, something like that. Negative 6 over 50, or negative 3 over 25. So that is the rate of change in radians per hour. Does that make sense? Does that make sense that this angle would actually be getting less? Well, it does, because remember, this rate of change in x is bigger than the rate of change in y. So over time, this triangle is going to look more and more like that. All right, I have a practice problem for you to do. Let's just do them one at a time. So we'll do one, then we'll go over it. So pause the video, please, and work this practice problem right here. Okay, let's see how you did. A vehicle is traveling 50 miles per hour west on the highway, crosses over a railroad crossing. Meanwhile, a train is approaching the same point from the north at a rate of 80 miles per hour from a distance of 200 miles away. All right, let's draw a picture. Traveling west, crosses a railroad crossing. And this is increasing in distance at a rate of 50 miles per hour. So I'm going to label this x, so this will be dx dt. Meanwhile, a train is approaching from the north 200 miles away. So it is approaching and getting closer to this point. So this is actually shrinking. Did you catch that? So it's shrinking at negative 80 miles per hour. Okay? And we want to find this. This is y, this is x, then this is z. We want to find dz dt. So x squared plus y squared equals z squared. So that's a 2x dx dt plus 2y dy dt equals 2z dz dt. All right, we'll just divide everything by 2. And we'll replace everything we need to know. Oh, well, we can't actually solve this one for any specific value, can we? Well, actually, we can because we are given a specific moment. A vehicle is traveling 50 miles per hour west on the highway, crosses over a railroad crossing. Meanwhile, a train is approaching the same point from the north. So x is 0. And then if you multiply that by dx dt, you're getting 50. And then plus y, well, that's 200 times the negative 80. And then z at this moment would have to be 200. So this is a negative 80 is equal to dz dt. Okay, I've got a practice problem for you. So would you please go ahead and give this one a try? All right, let's see how we did. The vehicle is traveling 50 miles per hour west on the highway, crosses over a railroad crossing. So this is our railroad crossing, which I'll just call C. And we're traveling this direction at 50 miles per hour. At that moment, a train that is 200 miles away is traveling this way at 80 miles per hour. So what we're going to say here is that the dx dt, x for the horizontal, is increasing. X is increasing at 50 miles per hour, but this length here, dy dt, is decreasing. So, yeah, y is decreasing here. Now, don't misunderstand me. I'm not saying that the velocity, usually we would think that velocity would be negative if you're moving to the left. That's certainly the case, but dx dt is actually the length. Dx dt, I'm letting x represent the length of this side, and y is the length of this side. All right, so this is x, this is y, and this is z. So we know that x squared plus y squared equals z squared. We could take the derivative with respect to time and get 2 x dx dt plus 2y dy dt equals 2z dz dt. And then we'll just simply divide everything by 2. All right. Now we'll plug in what we know. Well, we're looking for the rate of change in the distance between the vehicle and the train 1 hour after the car crosses the crossing. So if the car started at the crossing 1 hour later, if it's going 50 miles per hour, this x must be 50. dx dt is also 50. The train, if it's traveling 80 miles per hour for 1 hour and it was 200 miles away, is now only 120 miles away. And the rate of change, of course, is a negative 80 still. And we need to figure out z, but we know that this makes a right triangle. This is 50, 120. This is your 5, 12, 13, but all multiplied by 10. So this is 130 dz dt, and we're looking for that. So I'm going to just divide each term by 10. Kind of a slick move there, right? And then I'll just simply, let's see here, add these up. This is 250 minus, what is 80 times 12? Should be like 960, right? $980. All right, I think. No. That's not right. I did not do that right. 80 times 12. So 0, and then 1, 6, and then 0, 0, 8. Yeah, 960. 960. So we have 250 minus 960. So I'll take 960 minus 250, which is 710. So we have a negative 710 over 13 miles per hour. That is the rate of change in the distance between the two. I'm kind of curious what that is, so I will get a decimal on that. So that's 54. So 54 miles per hour. That is how close is the how quickly the distance is changing, of course. So that is interesting. All right, letter B. What is the rate of change in the angle formed by the highway, the vehicle, and the train at this time? Okay, so the highway, the vehicle, and the train. So here's the vehicle. The highway is this road, and the train is over here. So we're talking about theta right there. Well, we know actually all three of the rates have changed, so it doesn't really matter. I'm going to call this x and y. Let's use tangent. So the tangent of theta is equal to y over x. So the derivative of that would be secant squared theta d theta dt equals dy dt times x minus x times dy. Oop, I did that backwards. Low d high minus high d low. All over low low. So we got a whole lot of different things that we got to plug in here. We know that this was a 5, 12, 13, so that's the ratio that everything's in. And I can use that for my secant. Secant is cosine flipped over, so cosine would be 5 over 13. So flip it over, you get 13 over 5. Square it, so I'll just leave it as 13 squared over 5 squared for right now. And we got dy dt, which is the rate of change in the train, so that's a negative 80. The location of the car, or the distance of the car, is 50. And then y is the position of the train, which was 120. And then the rate of change in the car, which was also 50. All over the car's position squared. All right, well that actually gives us a little bit of help because we can divide each of these terms by a 50, which gets rid of that. And so then that makes this a negative 200 over 50. So that is not too bad at all. That's 13 squared over 5 squared d theta dt is equal to a negative 200 over 5, which is a negative 4. So d theta dt, when I multiply both sides by the reciprocal, I get 25 times negative 4 is a negative 100 over 13 squared, which is 169, and that is in radians per hour. Does it make sense that the angle is decreasing? Well, yeah, it sure does to me, because until this train actually reaches this crossover, the car is getting further away, the train's getting flat, the angle is getting more and more like that. All right, we got another practice. Oh, what do you know? Conical paper cups. Do the problem and pause the video, and then we'll go over it. A conical paper cup with a top radius of 4 centimeters and a height of 12 centimeters is filling with water at a rate of 3 centimeters cubed per second. What is the rate of change in the height of the water level when there is 8 pi cubic centimeters of water in the cup? All right, well, let's draw our little cup. We got a radius of 4. We got a height of 12. We know that they always have to be in that proportion. So at any moment, no matter what the level of water is, the radius and the height have to be in that proportion. So it looks to me that the height is 3 times the radius, always. So the height is equal to radius times 3. We're looking for the rate of change in the height of the water. So I need to express R in terms of H. So this will be, let me take the derivative of that formula. I get dV dt equals, oh, I'm not ready to do that because I was going to replace R with H over 3. Let's do that first. All right, so V is equal to, okay, H over 3. So squaring it gives me H squared over 9. So this is a 1 over 27 pi H squared times H is H cubed. Okay, let's get the derivative. dV dt is equal to 1 over 9 pi h squared dh dt. We're looking for the rate of change in the height of the water. We know that dV dt. We know that the cup is filling with water at a rate of 3 cubic centimeters per second, so that's 3. We need to know the h. Well, it's asking when there is 8 pi cubic centimeters. Well, we know that volume is equal to this in terms of h, so we'll say 8 pi equals 1 over 27 pi h cubed, so cancel out those. And I have 8 times 27 equals h cubed. So multiply both sides by 27. We'll take the cube root, and I can just take the cube root of each one of these separately, so that's 2 times 3 is 6. All right, so that becomes 6 squared, and then dH dt, which is what we're looking for. So our answer is going to be all this stuff. Well, this 6 squared is 36, and 36 divided by 9 is 4. So this is really just 3 over 4 pi is equal to dH dt. And that is in centimeters per second. Yeah. All right, we got another practice problem, a plane. So pause the video, give it a try. All right, let's see how we did. A plane is flying at an altitude of 4 miles, travels toward an observer at 600 miles per hour. What rate is the angle of elevation from the observer to the plane changing when the angle is pi over 4 radians? All right, so here's our observer. All right, the plane is flying at a constant altitude, so that's going to help us in this process, right, of 4. And we're looking for this angle, but keep in mind the plane is flying at a constant altitude, so that 600 miles per hour we can actually just put right here as the rate of change in this distance. So towards the observer, so this distance is getting smaller, and that's my dx dt, right? And then I got z here. So let's write a relationship. Let's use the constant and the rate of change that we know. So I'm going to use 4 and x. I could use tangent, and then it'd be 4 over x, but it would be, I think, better if I used cotangent, so which is adjacent over opposite. So cotangent of theta is x over 4. Then when I take the derivative, I'll get negative. The derivative of cotangent is negative cosecant squared theta d theta dt. And then this just becomes 1/4 dx dt. All right, we need to figure out cosecant. Oh, but they didn't tell. They told us the angle, not a certain distance. So we can actually just find negative cosecant squared of pi over 4. So this becomes negative 1 over the sine of pi over 4 squared d theta dt equals 1 over 4 times dx dt. Dx dt is a negative 600, right? All right, multiply both sides by sine squared of pi over 4. So I have d theta dt is equal to, we have negative 600 times the sine squared of pi over 4 all over 4. And it turns out that, that was a negative 1. The negatives canceled. It turns out you can just leave your answer like this. You don't actually even have to evaluate unit circle problems on a free response portion. You do on the multiple choice. There is quite several times where you need to be able to evaluate a unit circle value on the multiple choice section. So for fun, let's go ahead and practice. The sine of pi over 4 is the square root of 2 over 2. So when I square it, I get 2 over 4, which is 1/2. So this is 300 over 4. And that makes 75. So 75 is the d theta dt. 75. Wow, that sounds like a lot. Oh, but that's radians per hour. Yeah, per hour. So that's, I guess it's not that much. Because you sit there and you watch a plane fly. You don't sit there watching the plane fly for an hour. And of course, 75 radians would be, many revolutions around, right? But that's what you get at the rate per hour. You could convert that to minutes if you wanted to. You'd have to, divide that by 60. And that would be I think, a more reasonable value to think about. All right, let's do practice 6.4. So again, pause the video, give it a try. Okay, on this one we have the sides of the rectangle shown are increasing in such a way that dz dt is equal to 1, dx dt is equal to 3 dy dt. At the moment when x equals 12 and y equals 5, what's the value of dx dt? Well, we know this. This is x squared plus y squared equals z squared. We'll take the derivative with respect to time. We get 2x equals 2x times dx dt plus 2y times dy dt equals 2z times dz dt. And I'm going to divide everything by 2. So goodbye, goodbye, and goodbye, because I divided each term by 2. All right, let's figure it out. We know that x is 12. We know that dx dt is 3 dy dt. Oh, very interesting. So 3 dy dt. Wonder how this is going to pan out. 5, right? And then dy dt, we know in that, okay? Okay, that makes sense. Now, what is z? Well, if this is x, if y is 5 and this is 12, that's 5, 12 is 13. So we know that's 13. And we said dz dt was 1, so that's just times 1. So I can solve this for dy dt, even though it's not what I was asked for. So that's 36 dy dt. Excuse me. 36 dy dt plus 5 dy dt equals 13. So that's 41 dy dt. So 13 over 41. And dx dt is 3 times that. So that's a 39 over 41. And that is the rate of change in dx dt, whatever units that happens to be. No, I am not going to restart right now. I am in the middle of doing calculus. Thank you very much, Windows. All right, you got another practice problem, so please pause the video and give it a try. All right, let's see how we did here. A 25-foot long arm of a crane is lowered towards the ground at a constant rate so that the angle of elevation of the arm theta is decreasing at 3 radians per minute. What is the rate of change of the height of the end of the arm when the arm is 24 feet above the ground? So, okay, so this is constant. We know the rate of change of theta, and we're trying to find the rate of change of the height of this here, which I'll call y. So a little bit different, a little different situation than before. We're used to finding rate changes in theta in this problem, but totally not a problem. So we need to use theta, and we need to use y, we need to use 25. So that is clearly going to be sine. The sine of theta is equal to the opposite y over the hypotenuse 25. And we'll take the derivative. We get cosine of theta, d theta dt, is equal to 1 over 25 dy dt. We're looking for dy dt, the rate of change in the height of the arm. We know that the arm is 24 feet above the ground. We know 3 radians per minute, so we can put that in there. So it's decreasing. So that's a -3 for d theta dt. Well, if this is 24 at this moment, right? At this moment, this is 24. Then our Pythagorean triple tells us this is 7, 24, 25. And so the cosine of theta must be 7 over 25 at this moment. And that is equal to 1 over 25 times dy dt. Multiply both sides by 25, and those go away. So it's a -21 feet per hour. It is hour, right? Oh, no, it's feet per minute. Feet per minute is the rate of change in that height. All right, got another one. Another man walking towards a light pole. We just love to walk towards light poles. All right, pause it, give it a try. Okay, so on this one, the height of the light pole is 24. We got a 6-foot tall person here. And so they're going to cast this shadow like that. We're looking for the rate of change of the shadow length. So what we're looking for is the shadow length, which is just from here to here. So there's X and then Y. So this triangle. These are two similar triangles. I've got 6 is the height of the little triangle. 24 is the height of the big triangle. The base of the little triangle is Y. The base of the big triangle is X plus Y. So if we cross multiply, you get 6x plus 6y equals 24y. So 6x equals 18y. We're looking for the rate of change of y. So let's go ahead and just solve this for y. And you'll get 1/3 x equals y. Take the derivative and you get 1/3 dx dt is equal to dy dt. Well, we know that this person is walking away from the light at 6 feet per minute. So dx is getting bigger. So 1/3 times 6 is equal to 2 feet per second. That shadow is getting longer by 2 feet per second. And that looks like that's it for this lesson. Okay, so that kind of finishes off related rate problems. So until I see you in the next lesson, take care.